Hello and welcome back. Alright, in the last video we took a few minutes and put together a very simple console application and a stripped down XNA game to demonstrate the use of a delegate. There really wasn't no dire need to use delegates in that demonstration, so those of you that are new to the concept of delegates were probably watching the video saying, okay, I kind of see what's going on, but I have no clue why you'd really want to do this, because with the knowledge you've already given me, I could have just coded it straight out. There was no real reason to make it so confusing. Well, there are reasons for delegates. That's the bottom line. There really are reasons. And in this video here, we're going to put together a bit of a more sophisticated application that will demonstrate a real use for delegates. Logan, before we get started, give them a little bit of history. How did this come about? Because this is a real world thing.
Right. Well, what we're about to demonstrate is the creation of a simple image processing application using the XNA Texture 2D type.
Okay.
And how this application came about is there was one weekend where I was working on some graphical assets in another example for XNA. And I found myself needing to edit some of the images. To begin with, I needed to take a certain image and replace the background color with transparency. Now, I didn't have any image editing applications at hand, and I'm not really much of an artistic guy, so I wouldn't have been able to use those applications very well to begin with.
Right.
Now, we had just looked at the Texture 2D type, and we had worked on accessing pixel information, because we, of course, had to cover that in the per pixel collision video. So we had to look at how we look at the pixels of a texture.
Right.
In this video, or in this image processing application, we're going to look at modifying the pixels of a texture.
Okay, so when you started putting this application together for your own personal use, for modifying the images that you were working with for another XNA example, you ran into an interesting scenario.
Well, I began with one action that I needed to have happen, the creation of transparency, basically punching out a color. I guess you could say keying would be the correct term.
Mm-hmm.
I needed to key out a color to transparent. And what this resulted in was a single method. I had written a method then that would take in a texture, it would break it down pixel by pixel and replace a specific color with transparent, an alpha value of 0. And all of that worked well as a single method. Everything was perfectly clean, perfectly efficient. Well, once I found that I could do keying, I needed to do a few other things, maybe changing some colors, changing an image to grayscale, a few different operations. So the first thing that came to mind was to take this method that could cause keying and copy the whole method, make a duplicate, and change that to do grayscale instead of keying.
Okay.
That worked well for the first few times, but I actually made several of these to do different operations. And I very quickly found that there was a lot of redundant code. As a matter of fact, what was happening, since there were several lines of code that handled things like making the texture, accessing the pixels, looping through the pixels, the only line that was changing was generally a single line. So I had all these different sets of methods, and the only line that was changing was the color operation per pixel.
Gotcha.
So in order to make this more efficient, I decided to take my image processing methods and make them very generic. I made them just pixel processing methods. Their only function was to load the image and gain pixel level access. Then I made this method take in a delegate where I could specify what actual pixel operation was to take place. Then I could code a bunch of very small methods where these methods only took in a color and returned a color. So they did just the per pixel operation only, which was generally 1 to 5 lines of code apiece. And then the main image reading engine could be left alone from that point on to the end of all I needed to put together.
Okay. So once again, a real world use for delegates in still a relatively simple application. So let's go ahead and put this together.
One thing I'd like to point out really quickly, though, is that the method that we'll be using to access the pixels is purely in software. And it is actually rather slow for large textures, meaning that this is not a viable real-time operation.
Right.
What we're about to show is very useful for a game or a utility, but can only be done efficiently at game load or as a separate application altogether that saves files.
Right.
And what I mean by that is, since we're reading the pixels in software, the operation is very slow, something you wouldn't want to do frame by frame. So just pointing that out ahead of time so that...
So this is more along the lines of a utility application that we're going to put together.
I mean, it is fast enough to run at game load, but if you have a lot of information to be processed, you might want to do that ahead of time, save the results to file, and simply load the generated result.
Right, or move over to the world of shaders. Okay, so let's go ahead and put this application together.
All right, well, let's begin a new project, and let's make this project, of course, an XNA 2.0 project, and the name will be Imager. So say OK to that. And we'll begin first by just a little bit of project setup. I want to first begin with the image that we'll actually use for editing. We'll make sure we get all of that set up and drawing before we take a look at the imager itself. So the image that we're going to use for this demonstration is the Ragnarok character.
So to give a little bit of props to Zach, this is the concept art piece that Zach put together for the Advanced Digital Production class, and he just completed it, and we thought, hey, this will be an excellent image for us to use because, well, as you guys will see, there's some colors in here and an alpha that's going to work very much to our benefit in the demonstration we're putting together.
Exactly. This makes a very good demonstration image because there are a lot of different colors within the image itself, and even though we can't see this in the picture viewer, there is an alpha. So basically everything that you see as the color white here is actually transparent.
That's right.
So I want to get this image set up inside of our game. So I'm simply going to copy the image. And inside of our game, let me make you know what, I'm actually going to forego the creation of the textures folder since we have the content subproject, and I'm simply going to paste the new image into the content subproject. So this is where our image will live.
Okay.
Now to get this set up for drawing, let's get that loaded in, and let's make a texture field inside of our game to store it. So I'm going to make a texture 2D field, keep this simple and call it texture, because it's going to be the only texture. Then in load content, we can go ahead and load that texture in. So texture will be equal to content.load. We are loading in a type of texture 2D, and the asset name will be Ragnarok. And now that we have that loaded, I'll spend just a moment in the draw method, and we'll draw that texture to the screen. So we'll use the given sprite batch. We'll tell it to begin. Then we'll draw the image to the screen with a call to draw, where we are drawing the texture reference. We'll give it a position of vector 2.0, and we'll draw using the color white. Not wheat, but white. Once we have our texture drawn, we'll finish this all off with a call to spriteBatch.end. And let me build, check against errors. And now that this is built, I'll run very quickly just to make sure that we see our result in game. So we can see here that we do in fact have the Ragnarok image drawing, and this now underlines the fact that we're using an alpha here because we see the default cornflower blue coming in wherever we were seeing white before. So there is a very obvious alpha that we can see within the image itself.
Exactly.
And now that we have a base example to build upon, we can turn our attention to the imager class.
Okay.
So let me add a new folder, which we'll call classes. And inside of classes, I'll add a new item, which will be the new class. This class's name will be imager. Alright, with our new imager class, I'll begin by patching up the namespace a little bit. I'll take the class's sub namespace back off. The imager itself is going to be static, so I'll make sure we set that up as well. So we have static class imager. And before we delve too close into all the delegate side of things, I actually want to set up imager to be able to process a texture without using any delegates. I'll set up a simple scenario to kind of reproduce what I had done to begin with this imaging class, is just show from scratch what do we need to do to get the texture loaded in and some modifications made at the pixel level.
Okay.
So inside of the imager, we're going to make a method that is called process texture. So this will be a public method. So public static void process texture. Now process texture is going to need to take in a few things. And we'll go ahead and point one thing out about the nature of this method, and that it is heavily reliant on the texture 2D type in order to do all of the processing. And in order to use the texture 2D in that manner, I'm going to need a graphics device. Actually, I'll point out exactly why here. I think this specific implementation may not actually need the graphics device. It is needed whenever you make a new texture 2D, because we've seen in the past where we had done things like the star field, and in order to make a texture 2D from scratch, we needed a graphics device. So I'm going to specify a graphics device. So let's see, we've got... And before I specify graphics device, I probably need a few more usings.
Yeah,
I can go ahead and drop it in. The graphics device called device. But if we jump up to our usings, as now using Microsoft.xna.framework and framework.graphics. Suddenly we have access to graphics device. And the other thing I want to feed into this method is a texture 2D reference. So given a texture 2D called texture. Another thing to point out about this method is there is no texture returned. It actually operates on the texture given in. And I did this just for efficiency's sake, knowing that I generally wanted to take a texture and directly modify it, because if we were returning one, of course, we need a new copy made of that texture in order to return that and not modify the original. Alright, so the code inside of our processor is going to first need to look at the individual pixels. And to do that, it's useful to know how many pixels we have. So I'll begin with an integer called pixel count, which will set to a value of the texture's width by the texture's height. So given texture dot width times texture dot height. And once we know how many pixels we have, we can create a color array in order to store all of the data. So I'll make a color array called pixels, and we'll turn around and initialize that to a new color array of size pixel count. And now that we have an array set up for storing the data, we'll load all of the data out of the texture into that array. So we'll tell our texture to get data. We'll go ahead and type this data as color. And the array we wish to store it in is pixels. Now that we have all of the pixel information inside of an array, we can now loop through that element by element. So I'll begin a for loop, and we can tab to bring up the template. And we'll use I as our index variable, and we'll loop to a value of pixel count. So we'll loop through all pixels. Now for this part, like I said, before we get into the delegates aspect of the individual pixel operations, let's do a very simple one. Let's set it up so that as we go pixel by pixel, we omit any color that is not green. Let's set it up so that green is preserved, but all reds and all blues are shifted to 0. So what I'm going to do here is, since we're inside of our loop, we're looking at pixels. To look at the individual pixels, we'll look at pixels sub I, and then we can do something to it. Now, in order to modify it, really we need to make a new color from scratch, because of course the attributes, or excuse me, the properties like red, green, and blue, and so on, are read-only. So I'm actually going to make an entirely new color. Inside of that new color, now we can specify individual reds, greens, and blues because of the constructor of color. So we specify red, green, and blue for this image. Now, like I was saying, I want to preserve only green, so we'll directly set red to 0. For green, I'll take whatever the current green color of the current pixel is. So look at pixels sub I dot G, and for blue, we'll set that to 0. I do want to preserve the alpha, so that anything that's transparent will stay transparent. So we'll look at the pixel's current alpha, and we'll keep that. So once this is run, we should now have an array of possibly modified colors, and we need to store that back into the texture so that we can use it. So we'll take our texture, and tell it to run set data. We'll go ahead and type the data to color, and that the data we wish to set is from the pixels array. So now if there's no errors in the code, we should be able to build. And we should also be able to go back to our game now. Let's go back to load content, where we've loaded in our texture, and let's run the imaging texture process on this texture. So let's look into the imager class. We'll tell it to process a texture. We need a graphics device, so I'll specify the graphics device, and a texture 2D, which I'll give as texture. And remembering that texture is actually modified by the process texture method, we can go ahead and run. And we see this as a result.
Very interesting.
So everything has been shifted to green. So in cases where you're seeing things that were originally red, what's happening there is there are some values of white. It's not a pure red. There's a very little bit of green in order to lighten the overall color.
Values of green.
Exactly, values of green. But we can see that the entire image is in fact shifted over to green. So we've got a very obvious effect going on, which means that our processing is now working. We have made a pixel processor for texture 2D. One other thing I would like to note is at the moment it looks like graphics device is unnecessary, as it was not used in here.
Sure.
What this is from was, it actually, I guess this is a vestige of the original app that I had written. For that app, some of the things I had done required the creation of a brand new texture. Some of them were the procedural generation of the entire texture. And again, like we'd seen in the star field, we need the graphics device to make that texture.
Right.
Here, it doesn't look like we're going to use it at all, so I'll go ahead and make a very slight change to the method just to make the call more efficient. We can go ahead and wipe that out. Since we're not actually using the device, we'll simply take that out of the call, and we'll run just to verify that everything does indeed work just fine without a graphics device reference. But now that we have this set up, let me first show what the problem I ran into was. Now that this works, if we wanted to make a processor that, say, changed everything to red, or showed an alpha, or converted to grayscale, the easiest way is to simply copy the entire method, make a duplicate that does something else, like maybe process to grayscale. The problem is you end up with a lot of code duplicated. As a matter of fact, the only thing that would change was this line, because we could change to a different color. And that means all of the rest of the code is now redundant. So what I would rather do is set up a delegate that can be passed to process texture in order to handle the actual pixel color operation. So what I want to do is jump in here before we define the image or class and declare a delegate that can handle coloring a pixel. So I'm going to make a delegate that is going to have a return type of color. And the name of this delegate can be something like pixel processor. And pixel processor is going to need to take in some information. It's going to need to take in a color value. And we'll call this color value pixel, because in this case the way we're going to call this is on a pixel by pixel basis, meaning that we're looking at a current pixel with this value. Once we're done processing that pixel, we want to be able to gain access to the new modified information, and that's why we're returning color. So now that we have this delegate defined, let's create an example method that makes use of it. So we want to write a pixel color operation that matches the method signature of our delegate. So to begin, for this example, let's make a pixel processor that displays the alpha of the image. So instead of using the alpha for actual transparency, we'll instead show that value in the red, green, and blue components. So what I'll do is I'll make a public method, and I'm making this method public because we need to specify this method in the creation of the delegate, which is going to be done back in the game class. So we need to be able to see it from in-game. So this method is actually going to be public. It will be static to make it accessible in the same manner that the process texture method itself is. It is going to return a color so that we match our pixel processor delegate. The name will be called alpha, and we'll take in a color, again to match the method signature. And I'll name it pixel just to follow standard. Now inside of this alpha operation, we'll simply return a new color. And the values for this color are dependent on what operation we want to do. Here I'd like to see the alpha in the color components, so we'll set the red, green, and blue values equal to whatever the alpha component is. So that means we return pixel.a, so pixels alpha for red, pixels alpha for green, and pixels alpha for blue. And then I'll simply leave off I'll simply use the overload taking in only 3 components, and that way the alpha should default to completely opaque.
Okay.
And any non-transparent areas will just be, or excuse me, any transparent areas will simply be black. Now that this has been created, let's modify our process texture method to take in a delegate. So let's extend the parameters here to take in a pixel processor, which I'll simply call processor. Matter of fact, I'll just call it process. This is where naming gets a little bit tricky because, do we want to name this like an action or do we want to name this like a definition?
Right.
I'll just call it process in this case because that's how we'll use it when we call it. As a matter of fact, now that we're passing in a pixel processor, we can immediately turn around and use it in the pixel by pixel code instead of our hard-coded version. That means we could take in this new delegate process and we could tell it to process.
Yeah, and then send over that particular pixel sub I.
Exactly. Pixels sub I will contain one color element. Now, of course, in order to use this, that new color information needs to go back into the pixel it came from. So that means pixels sub I will actually be equal to the return result from this delegate. So here we do some generic process, given the color, and we store a new color back into that pixel. So with this now, we need to change our call to process texture back in the game. So back over here in game, where we're calling process texture, we also need to feed in a pixel processor. So to do this, we'll make a new pixel processor, and that pixel processor will encapsulate the method that is found within imager. So we have imager.alpha, that method we had created to process a single color. We make a new pixel processor to encapsulate that and feed that off to process texture as the delegate. So with this all, let me build, make sure that there's no errors, and let's run and see what the result is. Oh, very nice.
Very nice.
We have a grayscale looking image, which is the alpha being drawn in the color component. So now we can actually see the alpha used within this image.
I like the glass down at the bottom and up at the top.
Exactly. We have the little semi-transparent area for the bottom of the glass. So it is in fact doing a very nice job of showing us the alpha of that image. Now the key here, now that we have this infrastructure in place, it now makes it very quick and easy to write additional pixel processors. For example, let's say we wanted to make a pixel processor that will invert the given color, so we can invert an image color-wise. To do that, I'm actually going to begin by copying our current pixel processor, just so that we get the method signature in place. I'm going to change the name to invert. And to perform the invert operation, I'm actually going to store the pixels red, green, and blue components in bytes ahead of time, just to make it a little bit more clean when we put it back together into a new color. So we'll jump up a few lines and we'll begin with red. We want to invert the incoming red component. So I'll make a byte called red, or excuse me, R, and we'll set that equal to the given pixel's red, so pixel.r, and I will XOR it against 255. Now, of course, this alone is going to throw an error because the operation here isn't automatically casted to byte. So we'll do that explicitly. And now everything builds. Now, a quick explanation on exactly what we're doing here with exclusive OR is we're using XOR against 255 to invert whatever value is stored in the red component. And by invert, what I mean is flip any, if we looked at this number as binary, I want to flip any 1 to a 0 and any 0 to a 1. So we simply reverse the bits shown.
Right.
To get an idea of what that means, and the reason that we're using 255 instead of 0 or 1 or something that would seem to make more sense, is if you look at 255 in binary, knowing that we're working with a byte, so 8 individual bits, what that would actually look like in binary would be 8 ones. So something like that. And if we exclusive OR, well, the exclusive OR operation is going to work similar to the OR, only it's going to actually give the inversion effect, because in a standard OR operation, if you had a 1 and you ORed that with a 0, that would result in a 1. If you had a 0 ORed against a 0, then that would result in a 0. The key here, though, is with a standard OR, if you take a 1, ORed against a 1, then you get a 1. With exclusive OR, if you took 1 and XORed it against 0, that would act just like an OR-style operation, so you'd end up with a resulting 1. But if you XORed 1 against 1, that would actually invert to 0. So the key there is that it will actually invert. It will basically flip a 1 to a 0 or a 0 to a 1.
That's right.
And it's that inversion that we want to take place here, because that way we can reverse the colors that appear within our image. So that would take care of the red component. Let me copy this line a few more times so we can do green and blue. So I'll make a second byte called G, and that will be the green component XORed against 255, and a B variable, and that will be the blue component XORed against 255. So now we have all the information we need to assemble our new color. So we can take a look at the red, green, and blue, which will be the variables R, G, and B. Now, I would like to preserve the original alpha that came with the image. So transparent things stay transparent. It's only colors that get inverted. So we'll simply pass through the original pixel's alpha value. So with this, I'll build very quickly, make sure I have no simple syntax errors. Then back in our game's class, we could change the pixel processor from alpha to invert. And this gives us inverted colors.
Very cool.
So that's all nice looking, and the key here is now as we write these pixel processors, we focus only on the color operation itself.
That's right.
The only thing that has to be duplicated per se is the method signature, and that is essentially one line. Now there is one other thing that's very powerful that we gain by taking this approach, and since a pixel processor is specified out here when we make the call, that means we're free to write additional pixel processors elsewhere in code. Now of course that may not make sense immediately if we were the ones who had written this imager and the imager exists only inside of our code. But what if imager were more of a generic module, an assembly you would include? Maybe someone else wrote the imager, or maybe you want to hand the imager to someone else. And let's say they like the pixel processing functions you put together, but let's say they need a new one. So like, let's say for some reason we can't change imager or don't want to change imager, but we would like to specify a custom pixel processor not found in imager. Well, all we would really have to do is know about that pixel processor delegate and its method signature, and we're free to write our own pixel processors.
Okay.
To give a demonstration of that, I'll jump in right here, right below the load content method, though in actuality I would probably throw these methods near the top of the code just to keep things clean. But just to keep everything close together so we don't have to scroll a lot, let me write a custom pixel processor right here next to the load content method and then pass it along in our process texture. And just for an example that's very quick, I'm going to write a pixel processor that converts a BGR color to an RGB. And we'll do this operation by flipping the blue and red components.
Okay.
But since our image is already in RGB, it's actually going to make the colors wrong. But it is a very visual effect. So, to match our method signature, I'll make a private method. And we'll, of course, need to return a color type. The method name will be BGR2RGB. And we need to take in a color parameter. And we can again call this pixel, just for standard's sake. There. And the operation here is going to be very simple, so we can immediately set up our return. We'll return a new color. And the color's red component will be from the incoming blue. So pixel.b. The green component will be left alone, so we'll take our pixel's existing green component. And the pixel's red, or the new color's red component will come from the, or excuse me, blue component will come from the red. And in this case, I would like to preserve the original alpha, so we'll specify the pixel's alpha as the alpha. So again, the key here is we've simply reformulated a new color, swapping the blue and the red components.
Right.
Now, in our process texture call, we could replace the pixel processor with our new method. So we could replace this with BGR2RGB. So if we build, there are no errors. If we run, we get this effect.
Very cool.
Now suddenly the red colored character is now purple, and the yellow colored drink is now blue in color. So
yeah.
All of the reds and blues have been inverted, though you will note that the green leaves within the drink have retained their original color, which makes sense. We left the green channel alone.
That's right.
So since we have now proven that we're free to write whatever pixel processors we'd like, there's one more I'd like to show, because it's also actually kind of useful. Let's say we wanted to make a grayscale of the image and convert everything to a black and white image. The way we could do that is we could look at the red, green, and blue values and average them. Because of course we wouldn't want to separate it into individual channels. We could do that. We could look at only the red channel across all three, and we would indeed see a black and white image. Mm-hmm. The problem is it would only represent the red channel.
Right.
If we average all three channels together, then we can get a true grayscale. So, to begin with, and to speed the process, I'll copy our existing pixel processor. I'll paste that, and I'll change its name. We'll change this to grayscale. Now for the operation, I'm once again going to make a separate variable as we do the operation, just to make everything a little bit more clear as we put it together. I'm going to make a byte called value. If I get some spelling. I'm calling it value here because I no longer want to treat red, green, and blue as separate. In order to make the black and white image, the shades of gray, we're going to make sure that red, green, and blue are always the same value when we return them. So we're only worried about an overall value, a range of 0 to 255. So that will be equal to a result. I'm going to go ahead and cast that result over to byte, just knowing that we're going to need to do that after this math operation. So the values we wish to cast are all three components, red, green, and blue, averaged. So we'll take in the incoming pixels red, plus the pixels blue, plus the pixels green, and we'll take all of that together divided by 3. Then we'll take the overall operation, put that in parentheses so that we can cast the entire result over to byte before storing in the byte variable. And let me catch the terminator on that. Now that we have this value, let's specify that for the red, green, and blue components here in the new color. So we have a color of value, if I get some spelling once again. So value by value by value. And I will once again retain the original alpha, because if something was transparent in our colored image, we'll leave that transparent in the grayscale version. Now in our call to process texture, we can change the pixel processor over to grayscale. And now if we run, there we have a black and white version of our image.
Very
and of
nice.
course we also have the alpha preserved.
Outstanding.
And with that, that's really all I wanted to show in the example itself, just a handful of pixel processor functions contained within the imager, a few written custom out here in our main code, and also showing another use of delegates where we can make a pixel, I guess you could say an image preprocessor that we could use within the game. Again, I do want to stress the point that you don't want to do this real time for on a frame-by-frame basis. Now, if you find that the operation is actually getting too slow to use at the load of your game, let's say you have many textures or maybe an entire level's worth of textures to process at game load, one thing you could do is you could save the processed result, the processed texture 2D, to a file. So before we wrap this video up, I do want to show how we could go about doing that. If we go back into the imager, we can see here that the moment we set the data for the texture, we now have our new texture data. If we would like to get a copy of this as a file that we could turn around and use in a new project, we could simply tell the texture 2D instance to save a file of itself. So if we look at texture, we can look at that it has a save method. Save takes in two things, a file name and a format to use when saving. So for the file name, we could specify our temp directory, our working directory of the CS folder, and we could simply call this something like output.png. And I've named the file as PNG because I'm immediately going to turn around and specify an image file format of PNG. And you'll notice that there's actually several, but for our case we found PNG to work very well for control and color accuracy. So if we specify this and simply run our game, of course we still see the visual result because we are rendering that texture 2D, but now if we look at that folder, we have this new output PNG file. And if we load that, we can see that is our grayscaled version.
So now you can actually jump back and forth between original after modification.
Very nice. So again, just pointing that out in case the pixel processors you end up writing...
Now go ahead and throw invert back in there.
Make one with inverting?
So yeah, now all you got to do is just encapsulate invert, rerun, and close that out. Go back over to the CS folder and run. And again, before inversion, afterwards.
And of course, that being a standard PNG file, you're now free to load that into a new game and use it without further processing. So it might be more useful to make this entire utility as just that, a utility that you run beforehand.
Exactly.
But with that...
I think this does a much better job demonstrating the need of delegates, how they can be extremely powerful in the fact that they let you pass methods as parameters.
Exactly. So it's now at the point where we're passing functionality over to a method call.
Exactly. So from here, we're going to push things even further. It's now time for us to start talking about events and how delegates play their role in the whole concept of events, if you will. So with that, that is going to wrap up this video. Thanks a lot.